Most simple explanation is to say, well, the increase in resistivity is proportional to the length of the wire.
Increasing resistivity. Should that depend on the material, not the length? Is it degenerative?
I got it. Come on. Go. Get out of here. Go. Active shooters. Run.
Wait, am I gonna get... get taken down, bruh? Might get taken down.
Hello, Chris.
Hi.
Hi, how are you?
Not bad.
Okay, all right. I just saw what you sent me. That is from previous paper, right?
It's from the question that you sent me.
Genau, exactly. Yeah. Okay. All right. Good. I'll look at it and then I give you feedback. Huh? Next time.
Okay.
Then I can not now because we don't want to use the time for that. Huh? But I'm pretty sure it's all correct anyway. But nevertheless. Huh? Okay. So let me just. All right. Here we go. Because we have covered a lot of theory, a couple of questions. Now, of course, we really go into the past papers. So in due time, when you have time, you can send me the results for those questions. Now we go into questions paper, huh? For resistivity, actually. And I just give you this. And again, same thing. Multiple choice doesn't necessarily mean it's so simple. It may or may not be. Just a sec. So, could you read it already, Chris?
Yeah.
Okay, so
So resistance of P is 2/9 of the resistance of Q.
okay. Let me see, I have to make that a bit bigger. And why is that like that?
Because P has twice the length. That means on top, they're the same material, so the resistivity is the same. And also the diameter is 1/3. Oh wait, 1/3. So that means 1/3 squared is 1/9. So then that would be 9 times 2 is 18.
Okay.
So it's 18 times the resistance of Q.
Okay. So, in consequence?
They're in parallel, so they have the same potential difference. So, the current of P is
Just a sec. Sorry. Okay. Sorry. All right. Okay. Yep.
Current of P is a V over 18. Current of Q is V, just V.
Okay.
So 1 over 18 divided by 1 is 1 over 18.
Okay. Yeah. Exactly. All right. Good. Oh, all right. So yeah, that's correct. So you see, you can encounter quite a combination, right, of what we have dealt with in the theoretical part, so to speak, in the foundation. Now that it's being combined, and I would say, from my comment point of view, it's interesting actually what we encounter here in terms of questions, because it's how to say combining the various parts, which is not always the case in the questions. That makes it then like you need to know about like circuits and of course about, for example, in this case now resistivity, right, and how that links with diameter and length. So, but it's not only that; it's combined with the circuit question, and that's not so often actually. But this is good. That's why it's a good question. Okay, then here we go a bit more into kind of, well, I wouldn't say normal territory, but a bit more like we see some circuits and we see the, well, the resulting questions, right? So it's quite something actually what they combine here in the question. So the answer is coming to a very simple point, right? Is the temperature high or low, and is the light level high or low, right? So that is on its own simple enough, but of course to come to the conclusion is not that simple. So how do you proceed, or what is a good start? What do you think?
For the voltmeter T, from high to low, that means decrease in. So the thermistor's resistance increase. So the thermistor is lower in temperature.
Ah, okay. Let's go the goes from high to low, huh? The reading changes from high to low. What, when it's high, what does that mean? So the voltmeter is from the starting point, huh? When it's high.
That means the proportion of the resistor, that the resistance of the resistor has less of a proportion.
Okay, so what you say, if the voltmeter reads a high V, then the resistance is low.
No. If it has
okay,
higher voltage means higher resistance.
Yeah, good one. Yeah, exactly. Straightforward. Absolutely. All right. So now we have, having said that, what is the pattern, the behavior of the thermistor?
uh, when it has higher temperature than it has lower resistance.
Okay, good one. Now, if you combine the two statements you just made,
Oh, so higher?
yes, exactly. The tricky part, the let's say, yeah, let's say tricky part, is because we are getting told it's going from high to low.
Yeah.
But the key point is then the reading are both high. Yeah? So it's just basically coming to the starting point. So it's a bit like overkill of information, which we do not really need. But it may even lead us because we may stick to somehow, it changes from high to low. But that's not really the question, actually. We are looking at the questions when both readings are high, voltage wise. And that's all we need to know. So sometimes, I mean, there's a lot of writing, then there's a comparatively complex diagram circuit. But in the end, it's actually a simple, straightforward question, right?
Uh,
Both are high. Now, what does that mean for the temperature and the light level? So, to some degree, I'm exaggerating. This is a bit so not really needed. Of course, we have to think about it when it changes from high to low. What does that mean? But as it's about high, we basically have to disregard or can disregard the change because we know, like what you said actually, right? If the voltage is high, the resistance must be high. Straightforward. But then the thermistor is a different type. That means it goes exactly the other way around. So then you combine the thing based upon this statement. So therefore, what do you say about the temperature again, Chris? Just to repeat it.
uh, higher. No, wait.
No,
Uh, yeah,
it's
higher
correct.
temperature.
It's correct. Yep. Because you made the right two original statements combining, and now it's higher. So we are focusing on one of those two.
Yeah.
Now, independent of that, now we look at the second situation for the light for the LDR, right? So what is happening for with the resistance of an LDR
Increase.
increase, huh? So when we now are being told the reading on the VL, excuse me, is high, what is therefore the resistance of the LDR?
High. Also high.
Just go back to your original statement before, because
High.
we clearly decrease, right? Must be high intensity, which is correct before. I mean, your statement before.
The high voltage. It means high resistance, and then high resistance here is lower light level.
Exactly. Yeah, exactly. Good one. Low, huh? So in consequence, combining, that's what we get, huh? So
Yes.
in order to summarize, because it's a general rollout, and you don't have to learn that by heart, but of course you can put together the combination and say, okay, also first of all, voltage high, resistance high, right? That's something that was a starting point. And then we said, okay, the thermistor, let's say the has or the key point here is if the temperature goes up, what is the resistance of the thermistor? Ah, sorry, not the voltage. Temperature goes up for the thermistor. What did we say, or what did you say correctly happens to the resistance?
Lower.
Lower, exactly. And if we have the LDR, so let's follow the same pattern. the light intensity goes up.
Also lower resistance.
Here, you see, the bottom line is comparatively easy, right? Temperature goes up, resistance goes down. Light intensity goes up, resistance goes down. So they seem to have a similar behavior, but the way the question is phrased is going into the other direction, and that's why it says for the voltage to be high, the resistance must be low, right? Because of the other way around. So the core of the questions are, you can, how to say, from what we know, we can start to build, we can build up, and then just have to combine them, and of course be very clear what is one relationship, and then how are they linked, so what is happening, and then maybe we usually think temperature up, resistance down, but maybe the way it's phrased, it's about resistance going up. So we have to basically kind of invert that one. Still the same connection. That one goes up, that one goes down. But usually we look at it, maybe this one goes up and this one goes down. So we have to adjust a bit our thinking. Plus, because of the situation given. Plus, of course, then we have to link it as well with that one, because typically the resistance we have then to link it with the voltage. And then it's a question of what voltage reading are they talking about, right? Do they talk about a low voltage reading or a high voltage reading? Hence, of course, they behave then accordingly as well opposite. Then you have to link it properly. So it's more about having the basic facts in place, but then about the logical situation, to deduce it properly. Okay, so So in the application-wise, it's quite interesting. It's basically, how does a fire alarm system work, right? So at room temperature, it's 2000 ohms. So at room temperature. On the other hand, of course, we can always state this one. It may or may not be of help. In most cases, it is. And what is another? What else do we have to take into consideration, please?
The potential difference on the two components.
Okay. Exactly. Yep. Meaning? I mean, I know what you mean, but just to phrase it, to voice it out.
The potential difference on the thermistor.
Okay. Right. So, in other words, when you say, so what about the 12 volt? I mean, I know you're in the right direction. So what about the 12 volt?
12 volt. So 4.5 of the 12 volts have to be on the resistor, and the
good one, yeah.
7.5 on the thermistor.
So, in other words, you can quote, I mean, you don't have to, but just to say, Kirchhoff's second law, right, where we say the EMF, of course, is the sum of the PVs, right? So that means in that case, like we just said now, in values, the 12 volt must be equal to X, or resistance of P, or voltage of P, plus the volt, or X actually. No, that's a bad one. Let's say the voltage of the 150 ohm, something like that. And then it's, which is, of course, then the VT plus the 4.5. Hence, like you said, the VT is 7.5. So again, basic laws applied give us already a lot of information we most likely will need. before we go into the complexity of the question itself, right? Is there anything else we should consider? In terms of
No,
basic laws?
I don't think so.
Okay, so when we want to know the resistance of the thermistor, right?
Yeah.
So how do we calculate that? That's what I mean. Plus, we probably have to do an additional calculation before we can do that. But in its core, how do we get the resistance of the thermistor?
We have to make it so that the ratio of its resistance with the 150 ohm is the same as the ratio between 7.5 and 4.5.
Ah, okay. Yeah, can say it like that. It's an interesting approach. So let's do it like this. That we basically talk about the ratio, and the ratio is actually what you will need, right? So yeah, goes into the same. Um, and why is that the ratio is the same?
Because the resistance, higher resistance means higher voltage to it.
Yep. So yeah, that's correct. I mean, what we can say is, I mean, the ratio is that's one thing. But can you solve that question of the ratio? I mean, we can try, right? But and why? So you say V over I should be the same for both. So by both, I mean here and here, or
No.
okay. What is the same for both? Well, you may say it's a ratio actually, but
The
what is the
current.
same for both? The current, right? Exactly. Current is the same, right? So current is the same because it's a serial. So that means V over R, of course, if we go back to our calculation. And do we have the information for that? Can we calculate the current? Which is basically what you
Yeah.
said with the ratio, right? Kind of.
Yeah.
So what is there for that ratio, which is the current? For which one can we calculate it?
V over R. So 12. Wait, no. 4.5 over 150.
Exactly, because that's the one we know, right? Exactly. So that would be just 0.03 amps. Because this, of course, is now, as we say, the current is the same, doesn't matter, same. So we can, of course, utilize that information and then take the voltage which we have. So that's why ratio-wise we take the V over I, and then it's 0.03, yeah, which means 250 ohms. So of course you could actually express that I here as the same, and that's also neat, right? When you rearrange that and say, okay, that I is of course the ratio there between V and R, and they must be the same. So this ratio I have, this ratio I have that one, and of course I have that one on this side. So with this one, right? So following your argumentation line, which is fine. You could as well say, well, okay, I is the same because universal, also for the circuit universal. I go with V over R because it applies as well. However, of course, I talk about my ET and my RT. And in that regards, I don't know my RT because that's the one I need to know. But because the ratio is the same, so I can, of course, and that is therefore 0.03A, right? I mean, that's just another way to express it.
Yeah.
I mean, what you say coming from the ratio, which is more a mix between physics and math to some degree, because if you think about the ratios, which must be identical. On the other hand, you may say, that's where I came from, is to say, well, that ratio is actually the current. So if I look at the rearrangement of the typical Ohm's law, then of course I just have this one with the known entities to calculate the I insert it, and I get my 250 ohms. Same result, different path. That's important to keep in mind, huh? Because you see the argumentation is slightly different, right? Both make total sense. So that's why sometimes when you think about how to solve it, it's probably a good idea to follow that path instead of thinking maybe there's another way. Only when you see a solution, for example, a log scheme, they may or may not list both paths, right? And then you may have had one path, of course, still the same result. In the end, still 250 ohms, but it's a bit slightly differently argued, I mean, like what I said, along these lines. But you clearly operated with the ratios, which only as the next step follows something like that because of the ratio rearrangement, not because of thinking of the I. And then, of course, you have to clearly analyze the mark scheme and say, actually, just a different way. So that's sometimes a bit tedious. Not that you say, hey, wait a minute, I have the same result, but I have a different path. Have I made a mistake and by coincidence I have the right result? Or did I think along the same line, but maybe get slightly different in what I did, but of course coming to the same result because it's correct as well, the way I did it. Okay, so that would be C in that regards. Now comes a typical question, right, where we vary length and volume or length and diameter. And it's, of course, an interesting question. Typically, how does the dimensioning of the cable, for example, or the conductor influence the ratio of the resistance, right? In that case. So obviously, which one, or you could as well ask, which one has the higher resistance, right? Is X having the higher resistance or T or Y having the higher resistance, right? Without going into the calculation, Chris, guts feeling wise, which one would you say has the higher resistance?
X.
Most likely, huh? And why?
Because it's not half of it's not half of the cross-sectional area. It's less than half.
Yeah. What? Yes, that's one thing. You may say, you may argue as well. It's a good point as well, and say, well, basically, I look at a three-dimensional object which allows the flow of the electrons, right? It's like a cylinder, obviously, and clearly the volume of the cylinder is not, like you just said, is clearly less than half, and probably a quarter. So hence double in the end, depending on the dimensioning, right? That would be so that you say, and of course you can say like the big cross section is well PR square, right? So clearly goes with the square in it, and hence that 2D of course goes into double, right? Or one quarter then, so to speak, when you compare these two. Whereas these are only double. Of course that's linear, but that is not. So that would just be from a qualitative argumentation point, because sometimes you do not have to calculate it, like nothing like this. And also, like, you just have to give like what I just said, right? Just have to argue a bit and say, okay, I argue qualitatively along the lines of this because, like what you just said. Huh? So we can skip it because it's pretty clear in the end about how to do it. You just go by the resistance, right? And start to calculate it according to the value. Then you get the result. 2 to 1 is the Gauss feeling, right?
Yeah.
Okay, now not more interesting, very interesting actually as well, but now a bit more on the graphical part, the variation with the length. for two wires, right? Same material, the length of the wire, and how does the resistance behave? So without going into the question per se, what can you tell from the graph, Chris?
They have, well, the Y has less resistance for the same length.
Yeah. Okay. Yep. Right.
Half. So
half in that context. So because they behave, linear, right? So that's a nice. The 0.8 length is a good measuring point actually, because you clearly instantly see, like you say, double or half exactly. And how is now? You have some information, right? What does the graph show? So that's actually, like, we have to consider four different, totally quite different answers, right? So that's actually quite an. You have to think one by one. Have to go through.
the first two is wrong.
Okay. Why is the first one wrong?
Because cross-sectional area of X is half of cross-sectional area of Y.
Right. Okay. What about B?
They're the same material, so it's not
Okay. Yeah.
resistant.
That's a good. Yes. That's yeah. Just have to be attentive of what they say, but otherwise the experiment would make no sense, right? If we start basically, at least not to compare two different materials, then what is the purpose of comparing resistance over length, right? That's basically would be useless, because if the wire are different materials, of course they have different behavior anyway. So there's nothing to be said about what we really are interested in. Okay. Then what about C and D? So what about power? Maybe that's a good starting point. Huh? So how do you calculate the power?
Power is voltage times the current.
Okay. Yep. And when we look into our situation,
For X, because X has, if I set Y as the normal R, then R equals, so V equals Ri, then I has no change, and then
okay.
X is R is 2 times, so I would be half, and the power would be half.
Yes, exactly. Good one. All right, no, correct. So answer.
So it's wrong.
Yes, and which one? And answer which? Okay, yep, correct. Correct. It's wrong. And which one is now the remaining final answer?
Wait, actually, I think no. Because they're connected in series.
Mm-hmm. But you talked about D, right, Chris? What you just explained.
Oh yeah. Wait. I was explaining C, but I thought it was in parallel.
Okay. Okay. Okay, then maybe reassess briefly.
C is so in a series uh then the current is both the same, and for X, because it has double resistance, then it also has 2 times the potential difference than Y. So it has X has twice the power as Y. So it's
Okay, yeah,
correct.
all right. Okay, that's correct. That's correct. What you can think about it from the as a power equals voltage times current, um, because you would like to base, as we have these questions about power and resistance, right? Uh, because we look into the chart of the resistance. So we probably, I mean, you solved it in a good way. Another way is to think, okay, I mean, or maybe most, not, yeah, but again, slightly different, is to say, okay, when I look at V and I, and um, what, how can I bring in my resistance? Hmm? So how can you make power as a function of resistance or link to resistance? Or in other words, there's a second formula possible to calculate power, which we can deduce when we basically apply Ohm's law, make some substitution
Because I think V equals IR, so
formula.
V becomes IR, and
Yeah,
P equals I squared R.
yeah, exactly. So Ainsworth, you get exactly that one. So there you have a link then with the resistance. Then you can, of course, from that chart, as the resistance changes, then you can talk about the power formula. So there, for this one, you see the the easy link, right, with this one, and you can exclude the current because in both cases it's right anyway there. Okay, that's quite intensive, huh? With those, and let's see. I think it's a good one because it's that typical question about what about in the dark and what about in the light. Hmm. Now, here we have on one side, we have the charts, right? A, B, C, D. And we see obviously the potential difference, the voltage, obviously in volts. And it has kind of a certain limit value, right? The 1.5, so all across. But obviously a different pattern in terms of only very close to that max value, slight variation, or never reaches the max value, but still the same variation, kind of, but on a totally different level. And here, basically, well, never reaching the max value, but going to zero. And this one, reaching the max value, but not going to zero. So that is something may or may not be of help of what we have to consider. What do you have here as a configuration, basically? Like before, I didn't ask it before, but when you have these two potentials, what is that practical effect, basically? Or what we call that quite sometimes as well?
Huh?
You know, when you have, now we have the circuit, right? And we usually do not name it, but here it's quick, because the moment you have a variable one, we may have a bit a different name of how these two resistors act.
Like in series?
In series. I mean, it wouldn't be any difference to what we had here, actually. We just didn't discuss it there, but it's worthwhile to mention it now in this one. So in both cases, we have a fixed resistance, right, as you would expect usually, and a variable one. Now, instead of having a temperature-dependent one, we have a light-dependent one and a fixed one as well. So in both cases, how could we call that configuration as well? Because it quite often is used like that. So it's good that we are aware of that, not getting confused. Would you remember? Would you know it, Chris? Or
I forgot.
that's fine. That we would call a potential divider, which
Oh
is
yeah.
right. It's kind of obvious. Even if it have two resistors with fixed values, they're still kind of potential dividers, but we would usually not really use it because where we have a series, right? Then, well, of course, they divide the potential, but and it's then not so important. But of course, the key is that we have a variable one, right? So obviously, yeah, we vary it, right? Which has its impact then. And we want to know the potential difference, right? Obviously, because that's what the first kind of analysis shows us of those patterns, because we have identified which one is correct one. So, what would you say what situation should we look at? To separate, for example, maybe those who never reach that one and those who reach it. Variation is given for all, right? They all vary. So that, because then we can already narrow the field of answers, right?
So is it illuminated and then dark and then illuminated and dark?
For example, right? So when do you have? It may or may not be. That will show when we go into the details. But what I want to drive at is, Chris, to say we have a situation where we have a variable resistor, okay, which is driven by bright or dark. And on the other hand, the behavior patterns are four options, of which we can see that two of them are reaching a max point and two don't. So what you could link it to was to say, well, hey, I have an EMF of 1.5. So how can I now utilize my knowledge, or what should I now think about?
I think for in the dark, when it's 1 million ohm, it's because it's 1000 to 5, so I think it's basically all the potential difference is at R.
Okay.
So it should be the ones with the touching 1.5.
Yeah, genau. Okay, good one. Yeah, exactly right. So that's how to narrow it down, basically to say, well, goes back to our EMF, right? And of course our potentials here. Excuse me, our potential differences. So, and henceforth, of course, is when we are obviously, yep, like what you just said. So we are saying, well, these ones we are not considering. And now, how about basic? What is now the main difference between A and B, Chris?
Uh, for A, it assumes that the R still has more resistance than the 5k ohm.
Okay.
On B, it's more accurate because now it's 1k ohm, and it's 1 to 5 means that it only gets 1/6 of the 1.5 potential difference EMF. I mean,
Okay. So yeah. Okay. Well, so which pattern would you say is it according to that?
B.
B, right? Okay. Now, and that's correct. Yep. Now, what we can say is because what is helpful in this case um, is to think about the potential divider equation. No? So it comes with the potential divider. That's one thing. And we have the potential divider equation, which is not really something new. Um, but we are, how to say, um, when we write it down, because the intention is not to go into the why the equations like that, but we see it a bit why it is. Yeah? So we have, of course, the voltage, right, of the EMF. And basically, what we talk about is like that. Huh? So R1, of course, we can as well call it is the resistance over the LDR. So that would be important to mention. R1, and this is R2, is the fixed one. Huh? So it's the ratio of the variable one compared to the sum of both resistances. Have you encountered that equation, Chris?
Uh, no, but I think I would. I probably use it.
Yeah, you did. Yeah, that's a good one, right? So this is the explicit version of it, so to speak. Basically, you if now I like what you did. That's good. Um, you could as well like we say we know, right? We know this is like this, or this is like this one, etc. So we don't have to explain why. Just say, oh, same thing. We call up that one, Kirchhoff, and say like this. Same thing. We could just call up the potential divider equation as well in such a situation, and then deal with it accordingly. Yours is more on the qualitative kind of side, right? That you logically argue the way through. Of course, first eliminating does it reach the 1.5 and how does that happen? And then the second part is the variation, a small one or a big one. And this is good argumentation you did. So you could go into that one as well with this calculation, so to speak, and then go from there, right? It results in a similar approach because you utilize the values accordingly. What we can say is to say, hey, when we talk about that maximum got 1 million ohms, also, then what happens, right? That's one approach, right? Because we have a fixed resistor. So it's in that sense then a bit more kind of cookie cutter. That's usually the case, right? With these equations that you say, okay, but then you have to differentiate between two situations. And one situation is it's a high value or it's a low value. So your argumentation goes much more into the depths of the situation by trying to figure out what happens, right? Which is good. So, and nevertheless, to go quickly through it, I want to show that is to say, well, at 1 million, so 1 million ohms, we have the situation that we have the voltage is our EMF, so the potential difference is our 1.5 times the ratio 10 to the power of 6 divided by 10 to the power of 6 plus the 5,000. That gives approximately one, because that you see from the ratio, it's not quite, the important thing is here that, or interesting thing is here, you have this situation, but a slightly higher resistance. So it's not exactly 1.5, but close to. So in that regards, we can say it's approximately 1.5 volts.
Yeah.
By having the 1 million resistance. Now, if you go the other way around and say we just have the 1000, so at 1 kilo ohm actually, then of course basically same thing, 1.5, but of course we only have 1000 here, or we could as well say 10 to the power of 3. Let's do it like that. Looks nicer in comparison to the one on top. 10 to the power of 3 over 10 to the power of 3, and of course still the 5,000. So in other words, of course, when the resistance in the variable one drops significantly, of course that one becomes more significant as well. Here it's neglectable nearly. That's why we can say it's basically still 1.5 volts. Here it becomes a very different dimension. That's why, of course, the other one is to write it as 1000, right? That makes it a bit more obvious that we say 1000 by divided by 1000 plus 5000, that becomes 6000, right? But sometimes it's nice to think in potential, also 10 to the power of. And that means, of course, it will significantly drop, but it will not drop to, so that means it will significantly drop because we already eliminated that situation of 0. That's the point. So there will be a significant drop. So the slight variation is out of question because we can see that the fixed resistor becomes much more dominant, or extremely dominant actually, and that hence the voltage or the potential difference drops significantly, but it is not reaching 0 because there's still 1 and it's still this plus 5000. So it would be, you would need a total different fixed resistor in order to drive it where we would never reach 0 actually, right? Unless we are generous and say this is like, because we see it here, we say it reaches 1.5 and we say it's very, very close to 1.5. So that one could only be very, very close to the 0 line, but not exactly. But if you apply the same logic and say, then it would have to be very, very large. So a very high resistor. For whatever reason, that would not even make sense anymore. But just to follow that logic back. Is that okay with this one, Chris?
Yeah.
Okay, so you see, if you say this is the potential divider equation and I apply the values, of course, your answer will be very fast comparatively, right? Because you take two situations. That is the key point to say, of course, it's a variable resistor. So henceforth, I have to deal with these two different systems of very different resistances, which henceforth results in a potential divider because it has a totally different voltage, as you can see, 1.5 and 0.5. So it's variable from that point of view. And then we just apply it and then we can conclude it. Whereas the other one takes much more explanation, but it's good as well. So again, two different ways for the solution. Okay. I think this is not so interesting. Okay, that is, I would say, number 8, because we usually think of the opposites, right, for the thermistor. But there could be a situation, and LDR.
So lowest temperature and lowest illumination.
Yeah, good one. Okay. So that's on the other hand, now if you think about the basic pattern, then it just has to be opposite for both, in fact. Yeah. So it's less complicated in the end than it seems right now. Okay, this one is a good one because it combines again a bit the issue of the resistivity and a certain pattern of the circuit. So the same volume, huh? Okay, that's so okay, same resistor basically.
I think they have equal resistance.
Okay, good, yeah, correct. And why? What is your argumentation?
Since they have the same volume and they
Okay.
have the same length, then the sum of resistor, sum of the cross-sectional area of resistor Q should be the same as the cross-sectional area of resistor P.
Yeah, okay, yeah, all right. Okay, can argue like that, absolutely, yeah. So you can, well, again, I don't want to tell you, say, well, the resistance is given like that, so we can just apply it. Again, quite often these questions go that you have a basic relationships or formula, and then apply it to different situations, either extreme, like what we did before with the variable, going from a million to 1,000 ohms, for example, or like here, two different types. Then we just have to think it through of what happens. Huh? Okay, good. Now, here we go now, finally a bit into a different material. Same length, same resistance. However, the resistivity obviously varies. 1.7 times 10 to the power of minus 8 compared to 5.6 times 10 to the power of minus 8. So roughly factor 3 plus-ish. Huh?
I think that we don't have to change any units.
Nope. Okay.
So 1.7 times 10 to the power of negative 8 over, and then bracket 0.315 over 2, and then squared times pi is equal to 5.6 times 10 to the power of 8, to the power of negative 8 over, I just use x, bracket x over 2 squared times pi.
Okay, yep, all right. So, okay, let me recreate that. So we have the resistivity, 1.7 times 10 to the power of minus 8 over 0.315 squared by, we have the length, and we have 4 because of the quarter. So is that a reflection of what you said, Chris?
Yeah.
So what you could write, you said x half of d squared, because you want to look into diameter. So also then we, what I want to say is because of this one I can make it like this times pi, because I took it already. That's why I have the 4 because of the d half, and I took it out already. Is that okay?
Yeah.
Okay, all right. So in terms of math, of course, that is now becoming basically what it can take out. So how would you simplify now this one?
The 4, pi, and L are removed.
Yup, exactly. Okay, make life easy wherever you can. Exactly, especially in math. That is always the aim. Okay, so of course, exactly what we expected, like you said before. Basically, we have a situation of where we put the resistivity in ratio to the radius compared to the other material. We could even take out the 10 to the power of minus 8, actually, right? When you look at that value point of view. And divided by d squared, right? And then life suddenly becomes very easy, huh? Then we just rearrange and get it. So what is the rearrangement, Chris, for the diameter?
So square root 5.6 times 0.315 squared.
Yep. Squared, yep.
Over 1.7.
Okay, yep. Okay, so straightforward calculation. That gives us 0.575 millimeters, huh? Okay, right. So I just wanted to go through that one because in the end, this is, I mean, it's completely correct what you say. And then, of course, in the end, it's just for equation first, and then start to eliminate whatever we can in order to make it as simple as possible. Of course, we could have already done it at that stage, of course. But that doesn't matter. And we don't even have to do it in the end. It's just typical math, as we say. The less complex, the better it is. So we in the end get a very simple relationship, right? Okay, good. So what we can do as well now, Chris, let me just, have another paper. Is that okay if we continue with another paper?
Huh?
I would now continue with some more questions to resistivity. Is that
Yeah.
okay?
Yeah.
Okay, but I just have to transfer it because let me go with this one. Okay, so this is considered a harder paper actually. So from a level of challenge, let's put it like that. But it's not sometimes always the same. So it depends a bit on personal situation, perception. Difficulty levels are not necessarily always the same. So I see as well sometimes somebody says, "Oh, that medium paper was really tough," but the hard paper is okay. And of course, others say, "Well, the medium paper is challenging but okay, and the hard paper was tough." So this is called a hard paper, but it does not necessarily mean it's ultimately really a hard paper for you. It really depends a bit. Huh? So we have very different configurations. And not even the same elements. So what do we have in A and B, Chris, basically? What is the main difference between the same? Sorry, let me rephrase my question. What is different between A and B, and what is the same between A and B?
What's different is that A is in parallel and B is in series. And what is the same is that the voltmeter is measuring the potential difference of the the light dependent resistor.
Okay, yeah, you may say so. Yeah, I was more like both contain an LDR, right? I mean, but they are arranged in different, either serial and then parallel. And what about C and D?
What's different is that the voltmeter is measuring. On C, it's not measuring the thermistor. On D, it is measuring the thermistor.
Yeah, right. Exactly. And you see, right, to make it a bit more nasty, that they change the position, right? It's a detail, but you could as well have expected that this one is actually positioned here as well. Then, of course, it becomes even more obvious. So, a lot of these multiple choice questions deal a little bit as well with the rearrangement of patterns or of elements, which you could say for a good overview, of course, you would, of course, make it here as well, right? This one. We put this one not here, but here, then it's easy to compare and say, well, it's measured here and there, it's measured there. Just to say. Okay, now, in which circuit will the voltmeter reading an increase? So obviously only in one. How would you argue? Or where do you start your argumentation?
So temperature of the thermistor is reduced so that the resistance of the thermistor is increased. So on both A and B is wrong.
Okay.
And so we only look for when the voltmeter is measuring the thermistor. So D.
Okay, good. Okay. No, very good. Very. Okay, so it all, like you see, right? I mean, at first glance, it's, well, the variations. You have an LDR, you have the thermistor, you measure the voltage there, you measure the voltage here. But in the end, it's just about focusing on what is important, and that's the behavior of the elements. It always goes back to that, right? What is the behavior of a serial? What is the behavior of a parallel? What about the thermistor? What about the LDR? What about temperature up? What does that mean for the resistance? And of course, typically it's asked the other way around. Temperature goes down, so what happens? Huh? Okay. So we want to know the ratio of the diameter of the two different types of wires, huh? Alloy and copper. So how do we what could be a point to compare or to generate a ratio, actually? Let's put it like that.
We know that the resistance is the same, so we can think equal them.
Mm-hmm. Okay, all right, that's a good point. Yep. So RC is RA. I do it the other way around. I mean, it doesn't really matter, of course, but just because alloy is on top, so I shouldn't say resistance, actually, but we can say, no, let's say like this, yeah, as you said, the resistance is the same. So, okay, and how do we now come up with the resistance?
Diameter. So because alloy has the resistivity over the area, and then the copper has 2 times the resistivity. Wait, no, it's the other way around.
Okay, yep. So alloy has
alloy has two row.
yeah, exactly. Yeah. All right, okay. Let's put it like there. And of course over A. And the other one is just like that.
I think we have to add like differentiate the A, like make the symbol.
Okay.
Then
Good one.
the resistivity and the length cancels out.
Okay.
And area, cross-sectional area of alloy equals to twice the cross-sectional area of copper.
So as alloy, right? You
Yeah.
said, or copper. So alloy, is that
Yeah,
right?
alloy A is normal. And then copper is times 2.
Yup. So multiply like that.
Yeah.
Okay. All right. Good one. And what what are we driving at now?
I think we have to write the whole thing. So diameter. Uh,
I agree. But yeah, please.
I think because the ratio of diameter is the same as the ratio of radius, so do we just do pi times d squared.
You all can, right? I mean, what I would have said is to say, if you look at this one, right, and we are asked about the ratio of the diameter, what is the same thing? Ratio of the diameter is ultimately the same as what? If you extend it, so to speak.
Ratio of the cross-sectional area root square
Yeah,
root.
yeah, exactly right. I mean, what you or right, you can say that AA over AC is how much?
Equals 2.
2, right? Exactly.
Oh.
And and right, that's why because we are really on a good track to make it really simple. Yeah? What because you can make it really complicated, not complicated, complex, seemingly complex by introducing too early the whole formula. And quite often, part of keeping it comparatively simple is let's just go to the point, write it good, this is here, but just still keep it up and say, well, hey, if I have that AA is equals to double the AC, and I'm asked about the ratio, well, even if I don't have to think how's the link between area and diameter, I can just say, well, the only way I can generate a ratio is, of course, AA over AC, right? Otherwise, I don't get a ratio, right? Of course, I can always AA divided by 2, but obviously I'm talking about the division of two parameters and not with a fixed constant like 2, for example, or a constant, right? So then, therefore, I can just from that one already say, well, I'm looking for the ratio of two parameters or of the same parameter, but for two different materials. That's more accurately, ultimately, even. And of course, A is, of course, linked to diameter, right? Then, of course, I can extend it basically or expand it and say, what is AA? Chris, when you say, well, how can you link the area with the diameter? Straightforward.
Huh? I can't.
Because you want to make you don't you want to ultimately have because you are asked to give a number, right? If you
Yeah.
would not be given a number, you could leave it with that, right? And say, okay, that's the ratio. So it's the ratio between the two areas, and that's just times 2. So, or in other words, the area of copper has to be double the area of alloy for the same result. Yeah. Same length, same resistance, right? That's what we said. So in that case, the area of copper has to be double of that of alloy. And when you, without just physically thinking out, what does that really mean, Chris? What can you say about copper compared to alloy? So that you
Uh,
achieve that say, with the same length, the same resistance. I mean, I could ask you, what is the better conductor? That could be, for example, a question now. Is it alloy or
Copper.
copper?
The copper because it takes less. It doesn't need that much cross-sectional area.
Exactly, right? Or in other words, it needs double the cross-section area in order to have the same resistance as the alloy.
Yeah.
That's a simple conclusion, but you have to really look at it in order to conclude it. And that's why it's not really simple, actually. But it's the simple conclusion, which doesn't mean the way there is simple. That you say, well, factually, copper, yep, has only half the resistance, right? Or half the resistivity, actually. That's what we can say as well, because we say same length and it has the same resistance. But of course, somewhere there must be a difference, otherwise, yeah, we don't talk about two different materials, and that's what it is. But now, of course, being a multiple choice question, they don't give us that one, factor 2, for example, as the ratio between these two, or just show how they are interlinked in terms of, and then you come up with this one. That would be a perfect right answer, actually. Or you could go one step further and just put it as a ratio. But we have to select one of the values given, right? And of course, as we are given diameter, we cannot go for B because that's obviously the, well, cross-sectional area. So now how do we, just the last step, Chris, how do you transfer now or transform the area into the desired diameter that you include then? What do I have to do?
Square root.
Square root. That's just one, so just square root of 2. The reason why you do it, I mean, that you may have to show actually, also it's very obvious, right? That you say, like this one, right?
Yeah.
Okay. So that's why we always make it a bit simple, take the 4 out, etc., etc., and then have to do diameters like the dA, right? Half square, like that. Okay, yeah. So henceforth, we are going into A. Huh? Okay, so that is, of course, something it made, and like I said, if you start to introduce, you could, of course, replace already here, I mean, yeah, actually already here, that you go already not to that step, you already go to the next step, right? That you introduce already for A, the D, so the pi times D half square, and then the whole thing becomes, in terms of numbers, much bigger, right? Just visibly much bigger, which is not as easy to keep the oversight, whereas this one is very simple, right? At the moment we realized we could easily take that one out, and it becomes, within two steps, we already have basically the answer, right? Then the last step is just to say, well, they are related with the square, so it must be square root from 2. Because you will see in the solution in the mark scheme quite often actually that they exploded, meaning expanded already with everything, and then it becomes big formulas, and people lose oversight and don't really see anymore what's going on. With this one, you keep focused, so that's good. So there we have a block. I think this one is, I think this is more interesting. Yeah, let's take that one. And in relation to the time we have left, so the resistance of a metal cube, 2 parallel planes. Huh? So, okay. We say the connections to the cube have a negligible resistance, so basically it's the same. So how can we express the electrical resistance of the metal cube between X and Y?
I think so the resistivity times the V to the power of 1 over 3.
Okay.
And then over V to the power of 2 over 3.
Okay, can you say that once more, please, Chris?
The resistivity times V to the power of 1 over 3. And then that entire thing over V to the power of 2 over 3.
Okay.
Then after simplification is just the rho over v to the power of 1 over 3.
Exactly. And how do you come up so fast with the volume?
Because it's a cube, so the length would just be rooted by the power of 3.
Okay. Yep. Okay. Good one. So yeah, that. So how do you compare now the so-called the one we did before, medium, and this one so-called hard? Equal, harder, easier?
I think it takes more steps.
For which one?
The harder one takes more steps.
Yeah, right. Huh? So it's a bit. It's so you would perceive it as more as a harder comparatively still. Huh?
Yeah.
Okay. All right. Okay. Good to know. It's important for me to know. Okay. Good. But still, I mean, the way you approach it is good. I like. I think the the how the sense of a solution approach helps, of course. Yes, it's more steps, but it's so you have to think a bit. How do I go from A to D, for example? So what are the steps in between, and what is even D? Sometimes even, but then structuring it along the way, that makes it very manageable. Some of the students stumble then, right? They may see the D of where to go, but those steps in between are maybe a bit more difficult to handle or even more complicated. So instead of they see the D, but actually it's like in G, and they see many more steps even in between. Like this one is for me a good example here that got very short to the point. Huh? Okay, for next time, Chris, uh, because we have done now a lot of those, what is the subject you would like to deal with?
Uh,
I mean, of course, what we have next is actually circuits. There's a lot. I mean, let me rephrase what I said. Um, we have done now a lot of resistivity, really focusing on resistivity and resistance, less as part of circuits per se. Yes, in some cases they were involved, but that was not the main focus really. And it was always about the answer of themselves. The next one would now be to really go into a lot of various type of circuits, right? Parallel, serial, combinations of them, computations, variable resistors, etc. That's what we would do next time from my perspective. So, what about you?
yeah, just
Okay, okay. Then we deal with that. Of course, we do a bit more. There's not so much theory because with practical circuits, we basically have covered everything in order to work on that. But we may first do one or two joint examples and then we go into typical questions. Huh?
yeah,
Okay, all right. Thank you. Then thank you, Chris, and see you next Friday. Huh? Have a good week.
yeah. See.
Thank you.
Oh, that was brain. Mm, gamer night, gamer night, gamer night, gamer night. Oh man. One 606 1609 1690. 我经常我小妹，我钱毛你玩，嘿呀，王虎明。Chris the man. Yeah. Oh, I left. That's why I lost the rock, paper, scissors. Ah, no! Oh my god.